Good afternoon. My name is Bhavya. I work at NASA, and I'm super excited to be moderating this panel of experts. As you all know, this morning, NASA Administrator Senator Nelson spoke to the Humans to Mars conference attendees, and one question he posed is, what is the propulsion system we use to get to Mars? This panel gets to actually answer that question. So we have Patrick Frye from Aerojet Rocketdyne, who is the Director of Business Development. We have Jonathan Witter, who is the Chief Engineer for Advanced Technology Division at BWXT. We have Tom Martin, who is the Director of Propulsion at Blue Origin. And my colleague at NASA, we have Anthony Calomino, who is a Senior Nuclear Technology Portfolio Manager. So we have this amazing group of experts, and I want to launch right into our questions. And audience, you are welcome to send questions. I'm told I will see them on the chat that I see on the right side of my screen. So let me start actually a question. Space nuclear power and propulsion, which is what we're talking about today, incorporates both power and propulsion, and clearly there are common elements. But let's separate out them for a moment and start with propulsion. So I want to start with 3 generic questions that I will ask all of you to weigh in on. Before we even talk about nuclear, Patrick, make the case for us. Why can we not go to Mars with chemical propulsion? What does nuclear give, and is it worth it?
Yeah, thank you. It's a combination of system mass and short transfer times in order to keep the cost and it reduces the crew risk, radiation exposure, 0G time during transit. And this is what you get when you add nuclear. It can be done with chemical, but it comes at again higher system mass cost. If you're looking at conjunction class missions, about 75% more mass needed to do chemical options. If you get to opposition class, which allow you the shorter stay times, it's about a 2x hit on mass. So the nuclear options allow you a longer launch window, and the other thing it adds, which is critical for reducing crew risk, is extensive abort capabilities with nuclear options, and allows you abort capabilities up into arrival at Mars in some scenarios, and that's kind of key in order to keep this initial missions very safe.
Jonathan, do you want to add something to what Patrick said, or disagree or agree with him?
Sure. No, I tend to agree. And as he's talking about the system mass is growing, what that means is that then the spacecraft actually grows as well. And so the assembly time to actually assemble the spacecraft to be able to perform the mission would also have a lot of time and a lot of launches from Earth to provide all that equipment up into space. So the spacecrafts themselves for a chemical propulsion system would tend to be much larger and require more multiple launches to assemble the vehicle and longer time assembling it. So that's another important contributor of what mass means and the specific impulse means to it for achieving those sort of shorter travel times. And now that there is more interest in achieving more of the opposition class shorter mission times, and then that just drives up the focus more on nuclear propulsion to get you there.
Got it. Anthony, do you have anything else to add or anything you want to reinforce?
No, I would agree with what has been said. I would add a couple points. And it follows off of what Jonathan said. It's multiple launches, and we have to recognize every launch has its risk, right? And so there's always the risk that a launch won't be successful. And what does that mean in terms of the requirements of assembling the system in space? And the fewer the launches that it takes to put the assets in space and that need to be assembled to go to Mars, the less risk that we're facing in terms of overall mission success. And then I would also want to add, and I guess Kurt's right. I mean, we could still travel in other technologies, but one of the missions I think that NASA should pay attention to, which is a good benefit, is expanding our capabilities. Right? It's not just meeting what we can do today and using the tools that we have in our toolbox to get that done, but it's also advancing those capabilities for future missions and looking forward to the fact that a nuclear propulsion capability, whether it's NEP or NTP, expands that exploration space that the agency, as well as the nation, can have available as we go into the future.
Yeah, I 100% agree with you. It isn't just about, getting to Mars. It's also about, being able to do more. So Patrick, both you and Jonathan, you use terms like opposition and conjunction class missions. Not everybody in the audience may know that. So if, Anthony, if I could turn to you and ask you, how and if do architectures, and maybe you could just start by describing what these opposition and conjunction class architectures mean, how do they change the answer that we just got, that nuclear is superior with respect to chemical and getting to Mars with respect to the criteria we just talked about?
Okay, so the conjunction class missions, conjunction is looking for that synodic alignment between Earth's orbit and Mars orbit, which allows for a low delta V, or a lower energy increase in velocity to get that trajectory accomplished. And typically that trajectory would result in orbiting Mars and then being in orbit around Mars for another on order about 2 years before that alignment reoccurs. And so if it's a conjunction class, yes, it can be accomplished with lower energy requirements, lower mass launched from Earth, but that also means that the astronauts are going to be away from Earth for a longer period of time, and they'll be exposed to higher levels of radiation for that mission. The opposition class mission is what we call a short stay mission to Mars, and you leave a little earlier. You need to have a higher velocity to catch up with Mars, and then you can do about a 30-day on-surface mission on Mars, and then leave and come back to Earth with a Venus flyby, and that would results in about a 250-day reduced stay for the humans that would be part of that mission. And so that also has benefits in terms of radiation and zero gravity effects, but it also requires significantly higher delta V's to get out of the Earth orbit and to head to Mars. And that's the reason that we look at those two. It really comes down to what we would need for the humans and for their health and risk. But the aspect of looking at that in terms of the propulsion systems, we're looking at these lower energy systems, each of them nuclear, electric, nuclear thermal, and even chemical, will compete differently depending on that mission. So as was offered, the 75% higher mass for an all-chemical stage compared to a nuclear stage is really for conjunction class, where we wouldn't need the energy to complete that mission. If we're going to go to these faster mission types for an opposition class, that mass differential between an all-chemical and a nuclear stage grows to 2 times or even higher, depending on what that architecture is.
Right. So one really core criterion you mentioned, Anthony, was sort of surface stay. How long do we want humans to be on the surface of Mars? And what I heard you say was, using an opposition class mission, we have a short stay, 30 days, which has all these advantages you mentioned. In a conjunction class, we have to stay a lot longer, which comes with its own challenges. But then on the other hand, I mean, that's the trades, right? On the other hand, an opposition class mission requires much higher delta Vs. So clearly, kind of two important criteria. I want to open this up to the rest of the panelists and ask a question. Other than the ones I just mentioned, what do you see as a criteria for deciding which propulsion system, whether it's nuclear electric propulsion or nuclear thermal propulsion or chemical, we will use to go to Mars? Because really, it's how we need to make this decision. We cannot kind of be bottom up here. We can't say, NTP is harder and easier in these ways, and NEP is harder and easier in these ways, and therefore we pick these. We kind of really need to be somewhat top down. And again, I mean, it's top down and bottom up at the same time. But we do need to talk about what are the criteria. What are we trying to do? Are we trying to maximize the amount of time we spend on the surface of Mars? Are we trying to reduce the costs? So can you weigh in? And again, this is a question for all of you. What do you see as the criteria we should be using to make decisions like which propulsion system to use to get to Mars? Kind of repeating Administrator Nelson's question this morning.
Hey, Bhavya, if you don't mind, I'll start. One, I think we should step back. I know we're at the Humans to Mars Summit, but I think we should step back and say, as a portfolio of technologies and capabilities, where does space nuclear propulsion and power apply across a bunch of different mission sets, not just, a human Mars mission, but how does it apply to the cislunar space? How does it apply to the national security community, as well as civil and commercial? And so look at, which of those technologies might have the broadest application to a wide variety of stakeholders, so that when we commit to make government investment, particularly of taxpayer dollars, that we're going to maximize that benefit to as many users as possible. So that would be my first suggestion, is that we take more of a holistic view when we talk SNPP.
Agreed, 100%. Jonathan and Patrick, any other criteria you'd like to add?
I'll jump in. In terms of specifically back to the humans, the human mission to Mars, and I kind of broke it down into four basic criteria. First and foremost is crew risk and safety. It'll be the number one criteria in terms of selecting which is the best the propulsion options. Then comes mission risk and complexity. Depends on it gets down to how much time and how much aggregation you have to do to get a stage ready to go, and just overall mission complexity. Then comes mission cost, which should be upfront but not ahead of the risk. And then development cost is part of the overall mission cost, and that's the mission cost picks up all the launch cost to again aggregate all the elements for the stages. And then finally the development time frame. How long is it going to take you to get there? And when you look at the different propulsion options, how many back to the development days, how many miracles are needed to be solved in order to make that one happen? And how real or how near at hand is it? Those would be the basic set of criteria.
Yeah, definitely.
Go ahead, Jonathan.
Yeah. I was going to say, I agree. You really need to have, it needs to be driven from the top with some sort of requirements that then can allow you to make the decisions on which are the best architectures or which are the best propulsion system to use. And I think Tom brings up a good point, that having a holistic view of perhaps other applications for the technology, which ones by advancing propulsion may be able to advance power for other purposes. So I know that's another part of our discussion today, is a little bit about surface power.
Yeah, and to build off that and kind of what Patrick said, right? Some of, I think the technologies are more portable, and some of them are mission specific and architecture dependent. And so the more the solution is, architecture and mission dependent, the less likely it is going to be more broadly applicable to different customer sets. So I think that, again, that's an important place for us to look, when we're talking holistically, is we're engineers, we know the rocket equation, we like to optimize for the specific mission, but to the extent that we can use technologies that can be used all over the place, I think it's better for our business, our industry as a whole.
Yeah, let me take a break from asking you questions of high-level questions and maybe turn to Anthony for a few minutes to maybe talk about some of these applications that Tom and others mentioned. Can you tell us a little bit about what NASA is doing in surface power and propulsion, and also what other agencies, DoD and others may be doing in this area? Just again to get to Tom's point that we need to kind of look broadly and see what are the touch points across various applications and users.
Sure. So NASA is obviously looking at the requirements for both lunar surface missions as well as Mars exploration missions. And one of the guiding principles as we look at that is synergies between the two, right? Not necessarily focusing on developing a capability that is going to work out well on the lunar surface, but then needs to be reinvented or redesigned for a mission for Mars. The two particular areas that we are looking at are obviously power and propulsion. Let me talk a little bit about the power side first, and then I can talk more about the propulsion side. When we look at the mission needs for the Foundation HAB and the initial operations on the lunar surface, the groups that we're working with have really identified that something in the 10 kilowatt class power range will satisfy their needs. They actually have a little bit less than that for their power requirements for their initial missions there.
Right.
And that 10 kilowatt actually is also a good fit for the short stay mission for Mars. So 10 kilowatts also provides the power that is needed on Mars. Although we would see that there is going to be the opportunity and probably a very near-term need for additional power on the lunar surface, we really want to be able to have that first capability that we develop and demonstrate one that fits Mars and the moon, not just the lunar operations. Part of what we've built into that is extensibility, or what we're calling extensibility and power. And that is to come up with a basic design that you can envision can be grown without major changes to that design, sort of grown in an engineering way to a higher power limit of 40 or 50 kilowatts for the lunar surface initiative. And still be able to retain that 10 kilowatt capability for the Mars operation. And that's a big part of our strategy right now and moving forward. Consistent with some of the more recent policy changes that have come out of the White House, we have principally focused on low enriched uranium solutions for this. Yes, higher enriched uranium can provide us with a lower mass solution, and mass is an important thing to be concerned about. Well, we found that through some studies that high assay, low enriched uranium solutions will work. There's not much of a mass penalty. We do take a little bit of a hit in terms of the technology maturity, so we'll have to get over that gap to get that mass savings back. Well, we think we can do that on the power side. And just other two aspects that I think are worth noting is we would like to make certain that where we have that opportunity, that whatever technology we are developing for these lower power surface operation systems, that we wire into it, or that we at least pay attention to what we're going to have for NEP, which is going to be on the megawatt level, right? Now that won't necessarily be the design. We don't expect it to be the design, but we are using moderators in some of the fuels, and we would like to be able to have some of those fuels, moderator materials, still be used in a higher power system. For nuclear thermal propulsion, NASA's had a few years now in terms of direct investment with nuclear thermal propulsion. Very challenging. We need to have a reactor that's going to operate at, let's just say, north of 2,900 degrees Kelvin. There aren't many materials that are still solid north of 2,800 degrees Kelvin. And of those materials that are, they have to be compatible with a nuclear environment. And so the selection of materials has really become a challenge. The fabrication, the manufacturing of it is a real challenge. And that also extends to the fuel forms. There's just not a lot of data out there in those temperature regions that we can draw from to really get a good feel. But we've got some solid investments that we feel in the next 3 years will buy down that risk and give us that information that we need on NTP. I think it's worth noting that nuclear thermal propulsion also has the interest for some of the DoD or strategic interests for security as well. And so wherever we have that opportunity, we engage DoD groups and we collaborate with them to make certain that we both are working on areas that complement our needs, and that we're both addressing where we can the investment needs of each other to get that done.
Right.
We do want to invest in NEP. NEP shows some really strong benefits for a Mars opposition class mission in terms of launch mass, and so it has a strong draw for us to look at that. But there are things that we know we need to address in terms of the power reactor, some of the power management and distribution systems, and things like that to really get a better information base that we can use and then compare to NTP to make sort of a down select decision as to what the right solution is for a NASA mission. And broadly, and the last thing I would say is we are fully on board and are taking as much advantage as we can of commercial engagement. Really see that is extremely important to keep industry engaged and to send out like design innovations to engage them in terms of their ideas, their thoughts. They've got a lot of experience with terrestrial systems to try and use or leverage that in our systems. And actually the focus on LEU fuel types has really actually enhanced that ability to engage industry in the things that we're doing. So
that's an amazing amount of work. So basically both NASA and DARPA are investing in nuclear propulsion. And actually one thing you didn't mention, Anthony, that I just recently read about in the media is that Defense Innovation Unit is also looking
yes.
for a commercial in-space power and propulsion option, which is pretty cool to hear about. And they're, as you said, kind of moving forward on a commercial note. Okay, so I want to take this break just to kind of address Tom's question about we do need to understand the lay of the land. Given the lay of the land, given that there have been White House directives, there was an executive order on nuclear power, which had both terrestrial and space components. There was a space policy directive, SPD 6, on space nuclear, in the context of, and then there's actually, as many of us know, there was a national security presidential memorandum on launch approval. So now there's actually a process in place that is led by the government, where private entities, but government and private entities know how to launch a nuclear system. So that's pretty exciting. So it seems the groundwork is done. Returning to the panel, Jonathan and Patrick, maybe if we can start with you, and then maybe Tom and Anthony, if you have some thoughts as well. Pick a system. How long do you think? That's maybe the long pole in the tent. How long do you think it'll take us to develop a propulsion system to get to Mars, and what are the steps?
Go ahead, John.
Go ahead. Sorry, go ahead.
Go ahead, Patrick.
Yeah.
Hey, while you're deciding who goes forward, can I say hi to my friend Tor? He's 4.5 years old and he's watching. And how exciting is it that we have a 4.5-year-old watching this panel and wanting to go to Mars? This is what it's all about, people. Hi, Tor. I love you.
He'll be the astronaut.
That's right.
Yes.
Okay. Let me go through the steps first and kind of give you some of my thoughts on the timeline. So it's a systems engineering based process, and you're looking at mission sets, operating time, life. You design the propulsion system, you refine the fuel, you test the fuel, and then the reactor prototype, and then look at the engineering of the non-nuclear engine components beyond the reactor prototype. You test those components, then you integrate this together as a power and propulsion system. You build and you build a certain qual test unit, you operate that, and then you integrate with the vehicle system. So those are the kind of the steps that need to occur. And one of the key ones is, again, you get to a prototype system test before you go on and do your cert and qual. And, they're working right now under NASA funding to work on the NTP prototype. That's about an 8-year process to get that done, or just into that about a year. And then another 4 to 5 years after that to get kind of the initial flight capability through its critical path and get that certain qual unit. And then a few years, you have build up your first set of engine stages and in the vehicle. And so we can be ready in the 2030s timeframe, kind of mid 2030s plus for this mission.
Right, I would agree. And it's a lot of that kind of takes commitment and wherewithal
Yes.
to stick with the program and actually advance the technologies, advance the TRL levels of following that systems engineering process. So having the wherewithal to stick with it and accept that there may be some setbacks along the way as you're developing the fuel forms or the systems with whatever test, and be adaptable to make adjustments to the concept design or the propulsion system, whichever it is, architecture for that to best meet the needs. Another part of that would be then too as well, how aggressive do you want to be with the performance for the system, which would give you the ultimate best, but would there be another pathway to kind of progress your way along there and achieve things sooner that may have let's say lower temperature needs is the biggest driver. Materials and temperatures are always the biggest drivers for any of these systems, whether it's thermal propulsion or electric propulsion. It always comes down to the mass of the system, the temperature of the system, and how well you can manage those temperatures and power densities. So perhaps another, and this has been the technical debate over the years of being involved with this, is what is the best pathway to go, and once that's been settled down, then stick with it.
Yeah.
Hey, Bhavya, if I could add a little bit, just a different perspective, right? DARPA's off. They've got their own program, working somewhat in conjunction with NASA, but that program, Draco, the demonstration rocket for agile cislunar operations, quite a mouthful. They're working an aggressive timeline to get to an in-flight demonstration of an NTP system in 2025. Clearly it's not intended to have all of the capabilities you would need or want for the operational system, but they've laid out, I think, a realistic and aggressive approach to at least demonstrate an NTP capability in the 2025 timeframe. So I think, again, it gets back to that question of, the propulsion systems versus, the big architectures. I think depending on how we want to view it, the certain propulsion systems might be available sooner than the systems they may integrate into. So I'd offer that perspective.
And with that too is then also exercising the policies and procedures for the ground logistics. So the launch approval process, working through that process getting through those wickets as well, because that's an important part of it. You can design the best system, but if you can't get it up into space in the first place with all the ground logistics that are needed, so exercising those logistics is another good thing to do.
Yeah. One point that you all made is sort of the need for aggressive investment. I was on a National Academy's committee earlier this year, and the report assessed that an aggressive NTP program could overcome, the challenges Anthony mentioned, the challenges you all mentioned, to achieve a baseline human mission to Mars. And interestingly, the report noted that because of low and intermittent funding over several decades, an NEP chem system may not be ready. It's unclear if it will be ready for a 2039 mission, even if an aggressive investment is executed. And of course, the other point the committee made was that there isn't enough information today to make a down select between NEP and NTP. So lots to do on the propulsion end. It's about, we're 30 minutes in. I want to switch to power for a little bit, but I just want to make sure, Anthony, if you want to bring up the rear and say make any final points on, how long it might take to develop a propulsion system to get to Mars.
I agree with right now NASA's notional schedule is 15 years to get to a human rated capability, and that's with a sustained and aggressive investment posture. And if that isn't there, then it's going to be longer. I want to kind of emphasize, I think, what Jonathan had pointed to, and I agree with him. That is, I call it scope creep, right? Sticking with what you are able to get to the point where you've developed it, and then all of a sudden somebody says, well, 850-second ISP is no longer good enough. You now need 900 seconds ISP to complete the mission. And for materials and structures guys, it literally is throw your hands up and you go back. So that always creates a setback for us. Finally, I think the last thing, my background is technology development and research. It's really what I've spent my career doing at NASA, and it's my passion. And I think whether it's NTP or NEP, they both have their technology challenges, and they'll both have fun areas for researchers and technologists to work in advanced. And so it's just getting the right system that fits our needs is the important part right now.
Well, that's well said, Anthony. Okay, so let's switch talk a little bit about power now. And Anthony, you've spoken a bit about what NASA is doing already. We obviously need power both on the surface of the moon. We need power on Mars. We also need in-space power for at least from NASA's perspective, for deep space science missions. Anthony, you've mentioned already the power levels that NASA is looking at, about under 10 kilowatts. Both for Mars and the moon. I just want to open the question up to Tom, Jonathan, and Patrick. What power levels do you think we should start with at the very least to make sure we have the power levels we may eventually want to have?
Well, I'll jump in first and just say a little bit. Some of that comes down to really what the plans for the is it a short-term mission base, or is it to build out an infrastructure for what other people may want to be doing things there? So that's where maybe some of the commercial interests may get involved with what sorts of power levels do they think they need for in situ mining or other resource developments, or even for making the habitat itself for a longer base kind of setup. And that would be, well, then how do you develop, almost like in the United States or other countries, when you're developing electric grid system, how do you build that out to meet the expansion needs of whatever your electricity loads are, and in a sensible way? So probably starting off with lower power levels at first, and then maybe, like Tom was saying, is leveraging into, well, if a mining company needs a megawatt of power, well, then that kind of megawatt scale is good for a nuclear electric propulsion, but it's also good for surface power needs.
Yeah, Jonathan, I can follow up on that. We're very interested in Blue Origin in terms of sustained operation on the lunar surface, and you look at the requirements to do meaningful things on the surface, like you said, in situ propellant production, mining, even just sustaining, crews of tens to hundreds of people. You start to quickly move from the 100 kilowatt class into much higher power levels. Mm-hmm. So, I don't think anybody's going to argue that the more power we can get, the better. It will be dependent on the overall evolution of the capabilities. But our main point is, our hope is that we focus on technologies that are extensible, that are able to grow to those higher power levels that we think will hopefully sooner than later be required, not pursue technologies that are kind of point solutions to where we can't evolve them, because we see hundreds of kilowatts growing to hopefully megawatts on the surface as we're doing more and more stuff on the surface.
Yeah, it's a good point, Tom. And I was just going to add, but you want to start 10 to 20, and it's a good place to start 10 to 20 kilowatts and make it doable, get your first systems fielded, but keep an eye on the future and where it can extend to. So you want to look at extended surface operations, and probably initially in the few hundred kilowatt class as you extend it out, and then you want to grow larger. So you want to make the right technology choices that minimize the amount of reinvestment that has to be made over and over again to kind of extend those capabilities.
Right. Yeah. So I completely agree that we need this extensibility from lower to higher power levels. But I think Moon has some additional issues. And again, I talk to I have friends who are who think about Artemis based on the Artemis Space Camp ABC, and who think about ISRU. But they also are talking about use of solar power and batteries, right? Since Moon is actually closer to the sun compared with Mars. Mars, the case for nuclear power is pretty clear. So the question is, given its proximity to the sun and the relative ease with which we can get tens of kilowatts from solar power or batteries, right, how do we make the case for nuclear power on the Moon?
I can start with that and let the others chime in or disagree. First off, it provides you continuous power, nuclear. It's less location dependent, especially given latitude on the Moon, as well as shadowed regions that you might want to go to for surface habitation. It's very extensible to Mars. Again, where you have similar issues with latitude, distance in this case, as well as dust. And then it's less susceptible to localized disturbances, surface activity, dust that gets kicked up. So there's a lot of good attributes for why to do nuclear power for the lunar surface.
Yeah, I'd actually absolutely agree with Patrick. I mean, all you have to do is look terrestrially at the challenges that solar and wind, because they're dependent on wind and whether it's light out, they produce constraints on the system versus having a solution that provides a level load. And particularly as we're looking at the operating through the lunar night, working in permanently shadowed craters, the ability to generate power independent of that solar resource, I think is going to be very important, especially longer term.
Yeah, it's like the old bumper stickers from the 70s or maybe now. Solar's all right, but nukes do it all night.
That's right.
Hey, that was a bumper sticker on my undergraduate room back at MIT. It was green. I still remember it on my door. Yes.
So if I just wanted to add to that just a couple. I agree with everything. I think strong cases were made across the board by all the other panelists as to why nuclear is the right fit for the lunar operation. And even in our mass studies, I mean, the 10 kilowatt class fission surface power system is still the mass competitive power for the surface of the Moon. And as we grow, right, we're talking about a couple hundred kilowatts eventually, and maybe, as Tom indicated, you get up to megawatts. Those nuclear systems, the mass of those nuclear systems are not going to grow anywhere near what you would have for these other conventional energy sources. And at some point in time, you have to just bite the bullet and get into it and begin to develop that capability. And the lunar surface operations is that opportunity for NASA, is to get that started.
Yeah, and Anthony, I think that's a good point. I mean, one of the other constraints that we've got to consider is, the mass of the reactors and how we actually get them down to the surface. And that's why, considering it within the overall transportation approach, right? So do we have landers that are large enough to land these reactors, and especially as we want them to grow? So, all of this is kind of coupled architectures, but we need to remember that we're ultimately constrained by the mass that we can actually put down on the surface. And so to the extent that we can grow the landers and bring more mass down, the more we can take advantage of these power systems.
And I want to just take this time to point out, it's like, we still need a 10 kilowatt class system for Mars, right? So even though we know we're going to have power, or we expect, or we see that there's going to be a higher power demand for for the moon. From NASA's perspective, we want to make sure that our initial investments is one that would fit both mission types.
Got it. So a few weeks ago, many of us were at the Space Symposium, and some colleagues of mine who are in the private sector asked me a question that I want to pose to you. The question that was asked of me is, why doesn't NASA just buy power on the moon? So instead of trying to develop, put out solicitations to develop a system and then, being the owner and operator of a nuclear power plant, why isn't NASA just saying, hey, industry, we want power on the moon in year X at X dollars per kilowatt hour? What are your thoughts on the US government purchasing power from the private sector as a service, as distinct for developing it using traditional contract mechanisms? And again, I'll open it up to any of you who would like to address that. I don't know, Tom, if you want to start.
Yeah, sure. I'll go for it. First off, I think, ultimately we would want to be providing a commercial service for power, as well as just about everything we want to do on the moon and ultimately going to Mars. I think it's a question of, what are the market conditions that would justify a commercial service? When is the technology sufficiently developed to support that commercial demand? And then we also got to look at how would that power capability integrate into the architecture, because most likely the power system isn't going to be sitting there independent, right? It's going to need commodities, logistics. So I think we'd have to think through all of that, but ultimately we definitely would want to get to the point where it's bought as a service, just like we do here on Earth. I think, again, it's just a question of when do the economics and the technology kind of close the business case.
Right. Jonathan, Patrick, any thoughts on that?
Yeah, no, I agree with Tom on that. It's just about when the infrastructure develops to the point that there's a real user need, and then you're at a point where you have to build it out as basically a grid system. If you're going to actually add users with separate facilities or adjoining modules to that habitat setup that's there initially.
Right, and if it were be like if you'd have different utilities providing it, if it really grows a lot, or maybe it could start out as kind of like the Tennessee Valley Authority is kind of like a pseudo government, pseudo private company running power generation for the Southeast. So there may be some opportunities like that to build it out. But again, it comes down to for a commercial investment, it's going to come down to the business model for that.
Awesome. Hey, so I'm starting to see lots of questions come in, which is very exciting. Before we switch to those, I just want to kind of close this particular question out with Anthony. Anthony is a nuclear point person at NASA. You're like, what is she going to ask? Are there any restrictions or any legal issues NASA has where we can't do that, where we can't just set a price?
No, not that I know of. It's not my field, but it, I've not heard of any. I think that one thought on the question itself is, NASA has a need for the power, and NASA would quote be its own customer for that power, for the initial missions. But part of our strategy is that, like most everything, we don't want to own the product, right? We want to be able to build that coral reef. We want to be able to anchor that investment and nurture it along so that it gets to the point where it is something that industry would have and be able to not just use themselves, but also provide back to the government. I think that's always been a consistent model that NASA's had. One of the interesting things that we do have, hopefully very soon, looking at getting a release out for a solicitation for designs from industry for the integrated power plant. And some of the folks that have talked about this, it's interesting because they've asked questions. They go, well, you say you need 10 kilowatts, but if we give you 30 kilowatts and we still hit your mass needs, can we sell the other 20? right? So they're already beginning to think commercial product from their own business model. So I do suspect that once we establish that coral reef and we anchor the capability, that the commercial growth in production and supply of power will be something will come naturally.
I love that metaphor, Anthony, coral reef. I just think that's fantastic, having dived at a few coral reefs. Yeah, I mean, setting up a coral reef on the moon and Mars would be pretty spectacular. Okay, so let's switch to some questions. A question for Patrick, and again, others can chime in as well, is how heavy is a 10 kilowatt reactor?
That's the reactor is one question. I'll put it on a percentage basis. Okay, so if we're and this is a one way to contrast NTP from fission surface power as we look at that. The reactor winds up being just the reactor relative to the rest of the system roughly about 10% of the whole power system mass. But when you get to and you get up to NEP class, it gets a little larger percentage because as that grows, but the rest of the radiator and everything else grows faster. And then for nuclear thermal propulsion, the engine system, the reactor is about 3/4 of the total mass. So that's really reactor dominant on the mass. But on the power system side, it's a critical element, but it's about 10% of the overall system mass, not including the shielding, of course.
Yeah, and Patrick, maybe one way to answer that very specifically, I think the draft RFP for fission surface power that NASA put out about a year ago, I think had a requirement for the landed mass to be 3,500 kilograms. So that's
right. So about 350 kilograms, right?
Yeah.
Right. Exactly. As a reactor designer, I agree with those kind of numbers.
and just to, and I was going to touch on this earlier, that when you take a look at NEP and the kind of the technology needs there, and it's not insignificant to really make that NEP crewed Mars mission work. You need to have and we'll go back in terms, and well, talk in terms of alpha, which is kilograms per kilowatt for the power system. The alpha needed to make that system effective is 10 kilograms per kilowatt. When you look at the again in the draft RFP, those requirements initially, the alpha in that case is a few hundred kilograms per kilowatt. So you have to get a lot lighter to make that NAP system work. A lot of that comes with economy of scale as you scale up, but a lot of it comes along with technology advancements that have to occur with the larger power system to make it lighter weight as well.
Got it. So the next question, I think maybe directed to Anthony, but others should jump in. Is the plan to eventually deploy single large system or build a large capacity out of small, about 10 kilowatt units? Seems the latter would have resiliency and graceful degradation built in.
So right now we're looking at both options. It is built into the solicitation that the design of the surface power system can have interconnectivity with other units, individual units, to provide higher power output. So if we're talking 50 kilowatts and maybe we're talking, 5-10 kilowatt level or 2 or 3, slightly higher power level, that has, as you said, that has a benefit in redundancy. It has a benefit in reliability in terms of the power needs that you can supply. Part of what we're also asking for in the design of those systems is for a fault tolerance in the design. That is that if we have a major component failure, that we're still able to produce something like 50% of the rated power of the power plant itself. I think when you begin to look at power growth beyond 50 kilowatts, certainly by the time you get to a 100 kilowatt system, it's a complexity of integration, and probably even you can run some reliability studies that would say it's more efficient to go to larger systems and to increase that power on the system itself. So that's one of the reasons why we've built into that solicitation is what would be the extensibility of that design from 10 kilowatts to say something like a 40 kilowatt system. That's kind of the growth extensibility that we would have in that power system. And we'll wait and see what industry has to offer. You know, we've posed, I think, a very challenging problem to industry. They seem very excited about it, and we're very anxious to see what they come back with as far as solutions.
Yeah, no, that is very exciting. I'm myself pretty excited about the ideas coming in. Anything to add, Patrick, Jonathan, and Tom, on that question around single versus modular systems, single large versus modular small?
Well, I think Patrick kind of touched on it, that I think the single systems ultimately are going to scale from a power to weight ratio a lot better as you start to move into those higher power regimes. So I think ultimately the solution is we'll get to more high power, fewer systems. I think it's just a question of, as Anthony kind of said, where's that crossover between mass, complexity, et cetera.
Right, and as you work with the lower power levels, getting some endurance runtime on those lower power systems that will also validate kind of like the materials endurance and the
Right.
if they're rotating or dynamic energy conversion systems, the lifetimes of those energy conversion systems, that builds into the reliability that you need to build into the higher power systems.
Yeah, that's a key point, because as this was with the draft RFP that had been released, the initial mission requirement duration was pretty modest, but had a goal to get to much longer timeframes. You really only prove that out till you actually build and start operating a lot of systems. We have a good extensive database on thermoelectrics for RTGs, which we're used to, and we can build on that. But this is new territory that you're looking at for the power conversion options and the rest of the system for FSP. So.
Understood. Another question is, if I understand it correctly, so
We may have lost Patrick.
Yeah, he said his cell phone might drop him.
he'll come back. So a question is, there was an S-Star 100 megawatt portable reactor designed by Lawrence Livermore National Labs. And the question is, could a 10 megawatt version be designed for transport to Mars?
Well, that's a good question. I'm not familiar with that system to be able to
Neither am I.
answer that very well. But I suppose someone could look at that and whether or not that 100 megawatt system was meant to be a terrestrial based application rather than a space-based application, and then how you could scale it down, and then whatever the mass of that would be, and I guess gets that alpha that Patrick mentioned. Now he's welcome back.
Sorry, my phone decided to kick me out, but I'm back in. Well, I'm sorry. Can you repeat the question, Bhavya?
It's about this 100 megawatt portable electric reactor designed by Lawrence Livermore, and then they're asking, could a 10 megawatt version be designed for Mars transport with less than 100 metric ton mass? And Anthony and I said, well, we don't know anything about that system, but maybe you might know something.
No, I don't know about that particular system. Yeah, and there might be some traceability there, but yeah, we'd have to look. I haven't looked at that particular system to see how traceable it is to this.
Jonathan, what I'd offer, right, again, looking more holistically in terms of common technologies, there appears to be a lot of effort going into terrestrial-based, micro reactors using, the low enriched uranium fuels that are looking to operate in that 10 plus megawatt. Again, obviously there's a lot of design aspects that aren't going to port well to a space application, but I would again argue that the more we can leverage a lot of the work that's being done on the terrestrial side from a technology and a capability perspective, the better for all of us. And that is where they're looking at that 10 plus megawatt type systems.
Yeah. And I think that the thing that kind of concerns me about the higher and higher, like multi-megawatt class scale of electric production, is that you really need to have a really high efficiency energy converter as possible, and you need a means of having a very high efficient radiator, because you're going to be rejecting megawatts of heat to space, and that's not easy to do. It's easy to water.
Yeah, no, and with the heat rejection for space, the name of the game is the temperature for the heat rejection, because salt heat of the fourth.
Yep.
So can I offer just a couple of maybe thoughts that haven't been offered, but although it was touched on by Jonathan earlier, one is creep scope. I mean, scope creep, right? It's like we don't need 10, we don't need 100 megawatts on Mars. We need a couple tens of kilowatts on the surface of Mars.
Right.
And there's just a really high risk to designing these big systems without first getting some experience with these smaller systems that we just really shouldn't engage. The other part, which is really very important to consider, but you wouldn't necessarily think about it being related, is currently the amount of mass that NASA's landed on the surface of the moon or on the surface of Mars is around a little over a metric ton, around the metric ton. Let's call it a metric ton. And that has pretty much pushed our EDL architecture to get that mass onto the surface of Mars. For human exploration, we're looking at landed payloads in the area of like 18 metric tons or 20 metric tons. And we're developing brand new EDL capabilities to get that done. And these capabilities haven't yet been demonstrated in that environment and would need to be demonstrated in the environment. We start talking about landing 100 metric tons on the surface of Mars. You can see how far out we are from looking at something like that. So it gets back to a comment I think that was said before, is it how is it that your capability fits into the overall mix of the mission, or the requirements of that mission, and making certain that you maintain something reasonable that doesn't push your requirements and doesn't result in scope creep.
I agree with you wholeheartedly, because you got to keep your eye on the ball and make the development requirements modest enough or doable enough, practical enough that you can get this done in a reasonable time frame for a reasonable cost, but with an eye on the future, how to make it extensible. But again, don't go too
I really want a home run, but I'm going to be happy if we could just get to first base. Yeah. Then I'll start looking at second.
Yeah, I mean, this makes sense in so many other domains that we kind of start baby steps. We start with a Model T before we get to a Ferrari, but somehow in nuclear we want to go to the we want to do the good stuff right away, and there is the learning not just in technology development. We don't even know. I mean, the launch approval process is very new, so we don't even know sort of our legal steps. So I think. I think we do need to kind of start small, but I think the key is making sure that there is that extensibility. So as we do go, we don't have to keep starting over each time, right? So that's kind of key in my mind. We are kind of coming towards the end of our time together. I'd actually hope that we would maybe all have about a minute each to end, but we don't have that much time. Does anybody have any burning comments that they had wanted to share that you would like to?
Yeah, Bobby, I did. We have talked a lot about the power. From a propulsion perspective, I think there's a lot we can learn from traditional propulsion development. If you look at engines like the RL-10, the Merlin, when you design an engine that is capable and meets mission needs, it tends to proliferate independent of the initial mission that it was envisioned for. So I'd hope again that we kind of look at some of this as a capability, not as a solution to a specific mission, and have that viewpoint as we look to where should we be investing relative to space nuclear propulsion and power. I think the traditional chemical engine business has a lot of examples on where you can do that.
And I just very quickly, I want to offer up now, just like a nuclear reactor does not a systems capability make, right? It's a critical subsystem. We need it. But when we start to look at the fact that for NTP, we need large cryogenic fluid management and storage capabilities for For NEP, we need the PCS, and we need other technologies that are going to make that capability work. So we talk a lot about the nuclear side of the gap or the needs, but it's important to recognize that there are a lot of other challenges that you need that are adjacent to that system, and they too grow, and they too can become more complex as you begin to look at higher power systems.
Yeah, that's a good point, Tom. And I would just reiterate that you want to take a look at modular approach too. So you want to build up a basic building block set. Again, on our NTP architectures that we've looked at, our basic building block could be configured in to either serve an opposition or a conjunction class mission. Different architectures building up out of a set of common elements. But you want to basically establish that capability first, and then be able to serve multiple different missions with that.
That's well said, Patrick. And I think with that, we should thank our audience for being part of the panel discussion. Thank you all so much for taking the time to talk. I'm hoping that this session was taped, because I need to go back and listen to it a couple of times to make sure I got everything. Thanks again, everyone, and please enjoy the rest of the conference, and see you soon.
Thank
All right.
you.
Appreciate it. Thanks.
Thank you. A lot of fun.
Bye.
Bye-bye.